Hi, everybody, and welcome to DataBytes, the lunchtime webinar series sponsored by the National Consortium for Data Science. Today's speaker is Shahriyar Nirjon. He's an assistant professor in the Department of Computer Science at the University of North Carolina, Chapel Hill. Nirjon is interested in building practical cyber-physical systems that involve embedded sensors and mobile devices, mobility and connectivity, and mobile data analytics. Research challenges that he looks at include practical issues in physical world sensing, user context and mobility, real-time issues and resource constraints of the embedded platform. And his work has applications in a lot of areas, including remote health and wellness monitoring and mobile health. Nirjon, he likes to be called Nirjon, by the way, even though it's his last name. He received his PhD from the University of Virginia in Charlottesville in 2014, and he's worked as a research scientist in the networking and mobility lab at the Hewlett-Packard Labs in Palo Alto, California. He was also a research intern at Microsoft Research in Redmond, Washington, and at Deutsche Telekom Lab in Los Altos, California. Several of his works have been highlighted in electronic and print media, including The Economist, The New Scientist, and the BBC. Today's talk is titled Privacy Analytics of Homegrown IoT Data, and it will last about 30 to 40 minutes, and we'll have time at the end for Q&A. The way we do it is type your questions into the chat box. We'll hold them until the end of the talk, and then I will read them back, and Nirjon can answer them for you. So without further ado, I want to introduce Nirjon and let him take it away.
All right. Thanks, Karen, for such a nice introduction. I mean, generous and nice. I hope everybody can hear me clearly.
Yeah, we can hear you well.
Okay, that's great. So yes, I'm Nirjon from Chapel Hill. Like Karen mentioned, I go by my last name because that's my nickname. It's a different naming convention we have in our country, and that's kind of the reason. In today's talk, a little bit of background of this talk. I mean, this project is funded by NCDS, and thanks to NCDS for that. And this work, the title of this work is Privacy Analytics of Homegrown IoT Data. It's quite a full, and project size-wise, there are a lot of different problems in there. I mean, privacy is a big issue. IoT is a challenging problem to solve. We have tremendous amount of data, and it's a huge project. But in today's talk, I'm going to talk about a little piece of it. I mean, we're not going to touch like all aspects of privacy or all aspects of IoT. We'll see what we deal with and what are the future plans for this project. So let's get started. So this is today's outline. I mean, I'm going to talk at first about a little bit about our research, what we do in our research lab here at UNC Chapel Hill in my lab, and try to connect the dots, like what have been done and how we are motivated to this kind of research. Next, I'm going to give some overview on IoT, the concept of IoT itself, because many of us have heard about IoT, but different people have different versions of their own definition. So what we mean by IoT, that's something we should clarify, and why it is happening now, and some applications that we are interested in. Then a big chunk of my talk will be about the project overview, approach, and results. There I'll be talking about the motivation of this work, issues, privacy issues that we are considering, examples of problems, and our approach, experiments, and results. So this is an overview of our research. We do research in our lab in mobile and network embedded systems, which has kind of evolved into a new field called IoT, which is the short form of Internet of Things. In general, in such systems, we see these two types of processing blocks. One is embedded sensor system of some kind that collects data, and there is another block, it's a sensor data processing system that processes those data. And these two blocks are connected via some communication link. It could be wired, it could be wireless. In IoT, it's mostly wireless and low power communication link like Bluetooth or something. Now, in our research, when we build embedded sensor system, sometimes we pick some off-the-shelf sensors like a stethoscope or a Kinect sensor or a pulse oximeter or some smartphones. Smartphones are always there in any of our projects. And sometimes we build our own custom sensing devices, like we have built in the past a smart earphone that can detect your heart rate when you are listening to music, or we have developed rings that can be used to detect gestures with fingers. And very recently we have created a headset, a smart headset that can detect cars on the street when a pedestrian is listening to music and not paying attention to the road. Now, all these different types of devices are collecting lots of different types of data and sending those data to some processing unit. And in our research, these data processors could be tiny little processors embedded into the sensor themselves, like the one shown on the top, or it could be some data can be processed inside the phone, but phone is not as capable as a high-end server or the cloud, so sometimes we need to do further processing of the data into the cloud. And in all these things, I mean, sensor systems, communication, data processing, there are several different research challenges, starting from sensor fusion, like combining different sensors, mobility, connectivity. How do we make sure that they're energy efficient, they're running in real time? How do we divide all these computation, like which part would be running on the phone, which part of the computation will run on the clouds? All these partitioning stuffs are done there. In this talk and also in my research, I'm very much interested in data analytics and issues with privacy, so I'm going to talk about that in this talk in the context of IoT and homegrown IoT data. So at first, let's define what is IoT. IoT is the Internet of Things short form, and this is my definition of IoT. I call IoT a fabric that is connecting every object in the world. So the devices, appliances, gadgets, or objects that used to be passive or dull and dumb, they are now becoming more and more intelligent. Like watches are no longer simple watches. We have smart watches that can detect do more than just give you time. Like it can tell your step, your calorie, your heart rate, and so on. So similarly, all these different types of things are popping up in the market, like smart bulb that you can control with your smartphone, smart plug that you can that gives you real-time energy usage, and you can turn on and off using your mobile phone and so on. So there are smart oven that you can program your coffee maker, smart thermostat learns your daily habit, and that's how it controls the temperature and so on. So all these smart devices are everywhere, including our homes. And the idea is that the idea in Internet of Things is that we'll take all these smart devices and connect them to each other through the Internet. So your smart oven would be able to talk to your smart bed and your smart coffee maker, and you can create applications such as like when you wake up in the morning from your smart bed, immediately the smart bed notifies the coffee maker and maybe the smart oven to turn on and start making coffee, making breakfast for you. So that's the future we are going towards. Now there are two ends or views of IoT. At one end, researchers are doing IoT devices and networks research. So there are lots of scientists who are building these smart devices like thermostats or smartwatch or smart glass, smartphones, smart rings, and so on. So those people are working on IoT devices and networks. And on the other hand, there are a whole bunch of people, researchers, scientists, who are working on the data analytics part of it. So in my lab, we do both. In our research, we do both. And we feel that both are important, equally important. And from an education perspective, we need to train students and next generation professionals who have understanding of both devices and also the data. Now, one question is, I mean, we always had data analytics, we always had devices, but why IoT is happening now, like in 2017? Why we are talking about IoT now? There are 5 reasons I can see why IoT is happening now. Number 1 is sensor technology has advanced so much that if you look at all these different types of sensors, like accelerometer that detects motion, pulse sensor that detects your heart rate, force sensors, tiny little cameras, look at the size of all these sensors. I mean, they have miniaturized, their power consumption is like so low that with a single battery they last for like several months. So and they are miniaturized, so they can be put inside very tiny little devices like a watch or a ring. So that has happened, and that is happening, still happening. I already talked about miniaturization of computers and low power wireless communication. This is the third thing. So I'd like to mention this low power wireless communication a little bit. I mean, because Bluetooth, we know Bluetooth for a while, but Bluetooth low energy came to the market like a few years ago, and earlier this year and 2016, there is a new kind of radio that's called low power long range radio, LoRa. It's not here, but it's similar to Bluetooth in terms of like powers, but it has a very long range. So the point is, all these different innovations, like now we can send data to a few kilometers far from the source of the data by spending a very low power, very low energy. So this has happened very recently. 10 years ago, we couldn't send data, send a lot of data without draining the battery so fast. But now we can do it. Now with Bluetooth low energy or radios like LoRa, with one battery, devices like smartwatches or sensor devices can transmit data for over 4 years with just one battery. It was not possible like a few years ago. And fourth and fifth thing are the mobile devices. I mean, we keep seeing that new mobile devices are coming to the market, and they are now more powerful. These days, we have mobile devices that have like 4 cores of CPUs inside them. They have GPUs inside them that we couldn't even think of like 10 years ago. And finally, the power of cloud. It's amazing. I mean, essentially, we can imagine that we have a computational and storage facility that is infinite, which was unthinkable before the invention of cloud. So all these 5 different techniques are used, or a subset of them are used in most IoT systems, and that's why IoT is happening now. A few examples of IoT data analytics. For example, I picked 3 most popular usages of IoT. One is push notification. I mean, if you have ever used this Target app, I think it's a Macy's app, sorry. I don't use this app. My wife probably uses. She loves to go and shop in Macy's. And if you use any kind of app like this and go to the store, you might have experienced that there is a pop-up message on your phone like, would you like to buy this? And you have like 30% discount and so on. So how is this happening? This is happening through a technology called nearables. So when you are near let's say a bag in a Macy's store, you are within 10 feet or 5 feet or whatever, within a certain near range, these devices, these smart tags attached to those objects would beacon you some advertisements or some coupons, and they're sending you push notifications. So this is a huge commercial market there for this nearable for beacons. A second type of IoT data analytics example is predictive maintenance. So many machines like elevators or fleet or trucks and drivers and so on, all these different machines and processes are now being monitored with IoT devices with tiny sensors connected to the cloud. And they can monitor the health. For example, Tyson Group, this company, monitors their lifts, their elevators with sensors. And not only they can detect whether or not this elevator is working perfectly, they can actually predict whether or not they're going to fail within, let's say, 2 months from now. And if you can do that, if you can predict whether or not an elevator or, let's say, a vehicle is going to fail within 2 months, you can fix it at a much lower cost. So this predictive maintenance is a huge market also for IoT data analytics. And a third thing is real-time stream analysis. A real-time stream analysis is more like a good example of it is when autonomous cars and autonomous trolleys, any kind of autonomous vehicles will be in the near future we'll be seeing in the streets of every city in the United States. All these different devices are communicating with each other within a very short range, but since these devices are, since these autonomous cars are, their speed is extremely high, data from one car to another car needs to reach within a very short period of time, in microseconds or even in nanoseconds. So how do we make sure that IoT data are streaming from one car, let's say the red car in the behind, to the red car in the front, in a guaranteed time? So we need to guarantee the time that takes for each data bit to go from this car behind to the car in front. So IoT also, people in IoT who are experienced in real-time data analytics, they are also looking at these kind of problems. Now let's shift to the problem that we are interested in and the subject matter of this talk, which is the privacy. I mean, in all these applications that I've talked so far, we'll see that in general with IoT, privacy is the biggest concern. Because so far we have only our computer connected to the internet, and we have so many different problems. I mean, all our information. We are always scared, like I'm typing a document and there will be a virus, or somebody might see hack into my computer and see everything. Now, in the future, where all devices of our home, like our lights, our doors, our music players, our smart plugs, and our coffee makers, our thermostats, when everything is connected to the internet, there is a big chance that, I mean, they're vulnerable to hacking also. And it's possible that somebody far away from my home is looking at all my data, is looking at all my activity, and he knows what I'm eating, he knows when I'm home, he knows when I'm not home. So this is scary, and we want to protect our privacy, and we want to make sure that we are safe in our home, but at the same time we want to use this new technology so that our life is comfortable, our quality of life increases. So that's the point. I mean, we want to use all these different technology, but making sure that our privacy is intact. How do we solve that problem? That's the big vision. In this particular talk and in this particular project, we are interested in home IoT, that is devices, IoT devices at home, and we are motivated by this proliferation of this new technology, this Amazon Echo type technology, which is basically a one hub concept. What that means is if you have an Amazon Echo device or an Echo Dot device or a Google Home device, or recently Apple, I think earlier this week, 2 days ago maybe, they have announced their HomePod. So the concept of all this one hub concept is that first of all, they are your personal assistant. I mean, traditionally when they first came into the market, they were like this. You can ask something to them. You can query something like, will it rain tomorrow? How's the weather? Set an alarm for this and that. So they ask. They answers your queries when you ask them, and they act as like a personal assistant. So that was like 2 years ago. But recently, what's happening here is that now all these hub devices, these Amazon Echo type devices, are connected to your IoT devices in home, and by giving voice commands, now you can turn on your lights, or you can change your thermostat setting, or you can, for example, order pizza, or you can order something in Amazon, and you can hire an Uber driver, and so there are all sorts of services and devices now you can control through these home hub devices. That's an advancement at one hand, but it's also scary, because I mean, when just by talking to a device you can control your light bulbs, or you can order some pizza, imagine that somebody pretending to be you can do the same. Or imagine that there is a TV in your home and it's saying, it happens to be saying order pizza, and automatically pizza being ordered, although you are not hungry, you are not interested in pizza at all. So these things are happening, and it could be potentially dangerous for even safety. Not only privacy, it could be also dangerous in terms of safety. So we have identified and tried to solve at least two vulnerabilities. Type 1, we call it overhearing. So these home hub devices like Amazon Echo, Google Home, they're always listening. That's their job. I mean, you don't have to push any button or anything. I mean, they're continuously listening. You interact with these devices like saying, Alexa, hire somebody, or Alexa, order a pizza. So you interact naturally with these devices. Now, it wakes up when it hears this word Alexa, but on the process, it's actually listening to everything all the time. And imagine that what could happen, I mean, since the microphone is always on, if somebody hacks into these devices, he's basically always listening to you. So this is overhearing problem. I mean, I want this device only to listen to the necessary and only that it is supposed to listen. I'm not interested, and I'm scared when these Amazon Echo devices listen to everything in my home. For example, it's sitting idly in the corner of the room, but my kid is crying and there is a TV show is going on. It's listening to all these things. So any intruder who hacked these devices now knows how many people are there in my home, how many kids I have, and watches my favorite TV show. So everything can be inferred if somebody hacks into these devices. So this is number one problem. So what we want in this case is shown on the bottom, like all the voice commands, it's fine. They should go to Amazon Echo devices because voice commands are supposed to go to these devices. But anything else like baby crying or any other sound like a TV sound or my ringtone or my ding sound of my calling bell or whatever, I want anything else to be suppressed. I don't want those kind of data to enter into Amazon Echo. So that was type 1, and now type 2, this is a second vulnerability, which is no personalization. So these devices, Amazon Echo type devices, they don't have any sense of personalization. They don't have any sense of owner. So what happens is, if you purchase an Amazon Echo device, you can talk to it, your wife can talk to it, your kid can talk to it, and even there is a TV and there is somebody speaking loudly, it also listens to that and it responds equally. So it doesn't have any sense like Alice is the actual owner of this device and Bob could be, for example, an intruder. A TV sound can be an intruder. So there is currently no way to actually enforce this personalization, this ownership onto Amazon Echo. So what we want is Alice's voice should go into this Amazon Echo device because Alice bought it. Alice is the owner of this device. And anything else like Bob's voice or a TV sound or anything should not enter into Amazon Echo. Now, these are real problems. I mean, we didn't make anything up. I mean, if you look at the newspapers, you see all these different interesting and scary news. Like Google is quietly recording everything you stop, and here's how you can delete it or stop it. So there are news like this. I mean, Google and Amazon Echo devices are constantly listening. That is kind of the first problem, first vulnerability that we were talking about. And in recent news, I saw this. I mean, you guys might be familiar with this. And there was a Burger King ad which just says, "Okay, Google, what is Burger King?" And what happens is that if you are watching that advertisement and you happen to have an Amazon Echo device in your home, your Amazon Echo device, your Google Home device wakes up and starts talking about Burger King. Look at this scenario. I mean, somebody inside the TV set, I mean, he is commanding your home devices, your Google Home, or your phone. Your phone also has this continuous listening issue. So this is scary, and Google had to take care of this, and Burger King had to stop this advertisement. Another thing we have seen, I mean, this is another interesting news. a girl, 6-year-old, she accidentally ordered a almost $200 dollhouse and 4 pounds of cookies using Amazon Alexa, because she was playing with a dollhouse and she casually said, I want a dollhouse. And Amazon Alexa just ordered it. And what happened is even funnier. I mean, this was the news, and in California, San Diego, in a TV channel, the news anchor was explaining this event to the audience. And when that guy in the TV news was saying like, hey, there was an event, recent news, a girl 6 accidentally ordered a dollhouse, it triggered more Amazon Echo devices in the audience's home, and it ordered a few more dollhouses, and that was even bigger mess. So this is interesting, this is funny, but at the same time this is scary, and this is an annoyance. There are even reports like kids are becoming like parents are concerned that their kids sometimes Amazon Echo is returning pornography, or kids are becoming lazy because whenever a parent says, hey, do this, they just talk to the Alexa, hey Alexa, do this for me. So kids are becoming lazy and rude and so on. So these are all different negative consequences, and lack of ownership of these Amazon Echo devices is the reason. So now our solution, let's see how we solve these problems. So we created this new device called Sound Sifter. It's an add-on device. It reads like this: a smart audio filter that puts users in control of deciding what should go into their home hub devices. So that's exactly what we want. Let's say in your home you have a TV, you have Alice, you have a baby crying, you have a ringtone, and this is Sound Sifter that we designed. It has its own microphone, it has its own AI and a database. It listens to everything, but it's programmable, it's smart, so it kind of filters out all 3 non-essential sounds, private sounds like a TV sound or a baby crying and a ringtone, and just lets the voice command enter into Amazon Echo. So that's the high-level thing. I mean, we did not create a new Amazon Echo. We created a Sound Sifter device that connects to Amazon Echo, and it's like a filter. It's like a intelligent, smart audio data filter. Now, the way you prepare this Sound Sifter is that you provide some examples of positive examples of sounds to this Sound Sifter device. Let's say you get the Sound Sifter from us, you teach it, for example, which is a positive sound, like Alice should talk for a few minutes, and train the system that this is a positive sound. And you can also train the system to know like what is a negative sound, like a TV sound or a baby sound or a ringtone sound. You can say exactly what are the sounds that you think private and should not go into Amazon Echo devices. And once you give examples of this, train the system is ready, system is programmed, and Sound Sifter then learns and stores features from the data. So Sound Sifter do not store any of your speech or any of your data. It extracts features from data and stores features of data. It doesn't store raw data. So it's by itself, it's not privacy. It's not compromising your privacy. Now, how this data processing in Sound Sifter works. So Sound Sifter performs this following 3 steps of data processing. Number 1 is separation. In the first step, when you have like all different four different sources of data, like a TV, a person, and so on, in step 1 you separate that. The sound source separation happens. We create 4 different sound sources out of one source. So when It's like when you have one microphone, it's recording everything it listens to. Now, in this step, we kind of separate them out. Like we create 4 independent sound stream. One has only Alice's voice, another one has only ringtone, another one has only TV, and so on. The step 2 is selection. So once we have separated them, we select the one that we need. So in this case, we need Alice's voice. We select that. In step 3, we clean Alice's voice further, because sometimes what happens is that even after cleaning and separation, there are tiny little residues of other types of sounds. So we kind of need to clean these sounds. So then we are ready, and so only Alice's voice then goes into Amazon Echo devices. It's a clean and selected sound. Your personal sounds, your sounds that are not supposed to go inside Amazon Echo are totally filtered out. So now it's the video demo time. I mean, we'll watch a video of this sound sifter, how it works, and it's a 2.5 minute video. And after the video, I'll come back and explain a little bit about the video. And Stephanie is going to take it over from here, and she's going to play the video. And we'll be back, and I'll explain more about the sound sifter's capability and algorithms and results. Okay, Stephanie, please go ahead.
Home is the most private place for a person. However, with the increase of continuous listening home hub devices like Google Home, Amazon Echo, we have limited control in what goes into them. Due to the lack of person identification, these devices are prone to intruder giving commands. As a result, there have been several reports about unwanted online orders. Moreover, this lack of person identification can have bad influence on kids. Because home hubs are continuously listening, they listen to different sounds around the house. For example, home appliances, people talking, baby crying, etc. And by accessing this sound, an intruder can infer several information like number or type of appliances being used, number of people, or even the presence of people in the house. As a solution, we introduce Sound Sifter. It is a programmable acoustic filter that connects to a home hub like Amazon Echo as an add-on device and performs sound source separation, identification, and filtering to identify sound that is relevant to the application. A user can program the system to configure the type of sound they consider as unwanted to prevent them to go into these home hubs. For example, in scenario 1, Tom programs the system such that the home hub device only responds to him. So, Alice is the intruder here. When Tom commands, Sound Sifter allows it to go into the home hub device. We are using a custom-built by Alexa as the home hub device for the Sound Sifter.
Alexa, what is the temperature?
In this case, Sound Sifter detects that the command belongs to Tom. So, both off-the-shelf Amazon Echo and our by Alexa respond to him.
Currently, in Chapel Hill, it's 18 degrees with cloudy skies. Tonight, you can look for clear skies with a low of 10 degrees.
But when Alice gives command, Sound Sifter prevents it to go into the home hub device, whereas traditional device responds to her. Alexa, what is the temperature? After classification, Sound Sifter detects that Alice is not a primary or authorized user. So, Sound Sifter prevents responding, whereas off-the-shelf Amazon Echo responds.
Right now in Chapel Hill, it's 18 degrees with cloudy skies. Tonight's forecast has clear skies with a low of 10 degrees.
In the second scenario, Tom is giving command to his home hub device while his phone is ringing. Traditional home hub devices listen to both the voice and the ringtone.
Alexa, what is the temperature?
From this, intruders can infer personal information like when Tom gets a phone call. Sound Sifter uses sound source separation and machine learning to separate Tom's voice from other sounds and only allows Tom's voice to reach the home hub devices.
Alexa, what is the temperature?
Notice that the ringtone has been removed from the sound stream completely.
Right now in Chapel Hill, it's 18 degrees with cloudy skies. Tonight's forecast has clear skies with a low of 10 degrees.
All right. I'm waiting for Stephanie to give me the ball back so that I can share my screen again.
Privileges back.
Okay.
Perfect.
So I guess I'm back, right? So let's talk about the algorithms. I mean, how all these things are happening behind the scene. So we already know there are 3 steps. In step 1, we separate the sound sources. So let's see how exactly that happens. I mean, in a very brief and high-level way. So imagine that there are 4 different sound sources, and you have just one microphone in your home or in your device. So because this microphone is physically close to one source, like TV, or farthest from the baby, it will hear different sounds differently. Now imagine that we can model this scenario like this. I mean, M1 stands for microphone 1, and S1, S2, S3, S4, they stand for each of these sources. And this coefficient kind of represents how, let's say, how strongly, how loudly you hear each of these different sources. So baby would be very weak sound, but the TV would be probably very strong. So that's why these coefficients will be different. But we can model this microphone, what this microphone listens to, like this. Now let's say we have a second microphone. We can similarly model this second microphone. It will also hear all these different sources, and this microphone is in the same room but in a slightly different location. So what happens in that case is it listens to all 4 sounds. It also listens to the TV. Both this microphone listens to the TV, but there is a little difference. So their coefficients will be a little different. So let's add a fourth one, a third one, and a fourth one. So if you take all these equations and form a matrix, then it looks something like this. I'm not going to go into the details of the math, just for the ordinary, at a high level overview of this would be like, we can formulate a set of equations from, if you have 4 different types of sources using 4 microphones, you can actually formulate these 4 sets of equations. And then in a matrix notation, you can write it as M equals A into F, and M is like the microphones, all microphones, and A is like the environmental response, and S is like all the sources. Now, since we want to separate the sources from the microphone sounds that we receive, and we kind of have to kind of estimate these coefficients of the environment, and if we can do that, we can separate these sources. So there are existing algorithms called independent component analysis, ICA in short, that we use, and we kind of modified that to fit our need, and we solve these equations. So the bottom line is, if you have a bunch of sources using an array of microphones and solving a bunch of equations, you can separate all these sources. It sounds difficult, but it's possible. So it's more like, let's say you pick up water from different ponds and mix them up, and then you've got a bucket of water, and then somebody tells you to separate every single atom of this bucket, and so that you can tell which atom of water came from which pond. This problem is as hard as that, but if we can mathematically form it, it's solvable. As a second step is selecting the desired sound source. So now that we have 4 separate sources, what we do is we compute some features from the data. So like we said before, we don't store data into our device, we deal with features. So from the data, we can extract some features. So what is the features? It's more like a signature of the data. For example, all baby crying sound will be similar and they will have a certain kind of pattern. So that's their feature. Similarly, every time Alice speaks, her voice is a specific pattern. So that is her feature. So we extract that feature from her voice. Similarly, we do that for the TV and for the ringtone. Finally, there is a matching step. We can match. We have a database and we match all the different sounds. So this database says which is a positive sound, which is a negative sound, and once we analyze all these, we match all these different sounds and see that only Alice's voice is a positive sound. So we take these and we reject all others. So that's how, by extracting features and matching features with the database, we kind of know which is the relevant sound and which one we should be selecting. Final step is about cleaning the selected sound. So in a traditional adaptive filter technology, how people clean sounds is that you have a signal and noise. This is a traditional way of doing that. You have signal, noise, and you have a filter that uses a model of the noise and they subtract that. So you have signal plus noise, you use a model of the noise, you subtract noise, so signal plus noise minus noise equals signal. So you get the signal. So that's the basic way of filtering any sound. In our case, in Sound Sifter, we have an advantage because after sound source separation, we already have the exact secondary sources, exact model of the noise. We don't need to model noise. We have the exact secondary sources. Like we know the ringtone, we know the baby, and we have a mixture of Alice's voice, a little bit of baby sound, a little bit of ringtone sound. So we can just use this and do a better job in cleaning the sound. That's the takeaway message from this. I mean, instead of using a model that could be wrong, we have an exact secondary source sound sources. That's why our approach is much better in terms of cleaning sounds. Now let's see how our system performs. We have developed the system, two systems actually. One is the custom home hub and another one is the sound sifter. The reason we have to develop our own custom home hub is because Amazon Echo devices do not have any audio jack in it, and we cannot really tamper with. It's not an open platform, so we cannot really inject or control what goes into it. So we kind of have to build our own Amazon Alexa based on something called Raspberry Pi. So this blue box is an Amazon Echo device that we built. You can think it like this. It is exactly identical in terms of performance and its capabilities. So the top one is homemade Amazon Alexa. You can think like that. And the bottom one is the sound sifter that we built. It has its own microphone and all the algorithms that we just talked. And if you look at this, carefully look at this fourth figure, this sound sifter, this green box actually sits on top of this blue box. So it's just like a cover. So we made it like a cover. Electronically, they are connected through using a wire, but aesthetically, we made it look so that it looks like a cover. And we compare our sound sifter with a regular Amazon Echo device, and these are our test cases. So we have 3 scenarios. In scenario 1, we have 15 participants. They are talking to Amazon Echo and at the same time sound sifter, and the noise level in the background is none. I mean, it's a regular background. There's no extreme noise. In the second scenario, we have music in the background so that we can test whether or not sounds are being kind of separated and cleaned and so on. We had 10 participants in that, and the third scenario, we test the personalization thing. I mean, whether or not Amazon Sound Sifter can only respond to one person, the owner. So we had 10 participants, one is the actual user, and we used 9 intruders so that the device only listens to the user, not the intruders. So this is result number 1. This is showing how long our Sound Sifter takes to process all the data, all the incoming data. Once you issue a voice command, it takes about 400 milliseconds. It's less than half a second to process all the data. If you look at the plot, I mean, these 3 steps: separation, identify, and removal are the 3 major steps I explained in this talk. We do have some additional steps for pre-processing that I skipped, but they're helping the other steps. So if you add up all these things up, they are about 400 milliseconds in total time, which is not really a big deal, I believe, unless you were really in a hurry to get the results. I'm not sure if it is too much of a big deal if an Amazon Echo responds 400 milliseconds delay, so I guess it's fine. Or it could be improved by throwing in more processing speed by using more capable Raspberry Pis and so on. This is an interesting result. It is the second set of results here. I'm showing that I'm comparing Amazon Alexa, Amazon Echo with Sound Sifter. So, and in 2 scenarios. The scenario 1, the normal voice mode, the background noise is normal, and the second is the noisy mode. I mean, there is a music in the background. So let's see what happens here. This left bar is the Amazon Echo, and the right bar is the Sound Sifter. When the background noise is really normal, regular background, both devices respond to equally. So we issued 50 voice commands to both devices, and they responded equally and correctly. So our device just works as fine as Amazon Alexa in that case. But when the situation is noisy, we see that Sound Sifter responds to 46 out of 50 commands, whereas Amazon Echo was not as good as Amazon Alexa. And the final result is like this, and this is the personalization result. So once again, we're comparing Amazon Echo with Sound Sifter, and we're trying to see whether or not it can detect the owner. We see that primary person, I mean the primary owner was detected when the primary owner was talking, both devices were detecting equally. When the intruder was talking, Sound Sifter was able to kind of catch all intruders, but whereas Amazon Echo could not, I mean, because it cannot. So it shows the power of a Sound Sifter, that it's really reliable in terms of filtering out unwanted sounds. So finally, I mean, the concluding remarks: we developed and evaluated Sound Sifter, which is an add-on device that filters unwanted sounds to mitigate overhearing. And we developed new algorithms for separation of sounds and cleaning of sounds. And in the future, we look forward to improve the hardware, make our sound even more cleaner, and explore other applications beyond voice and voice commands. So, all right, thank you for your attention, and if you have any questions, feel free to ask me now, or if you happen to have more questions, feel free to email me, and I'll be happy to answer.
Thank you, Nirjon, for that great talk. We only have a few minutes for questions here, so I'm going to read back what we have here. how much training does your sound sifter currently require? And in addition, how long would a user need to talk to the sound sifter for it to routinely identify their voice?
Yeah, that's a very good question. I mean, we get asked this question quite often. Any machine learning system, this is a headache. I mean, we need to train this system, a common sense approach for that is we train the system for every single type of sound. Like, let's say Alice is the primary user, so Alice needs to talk to the system for at least, essentially Alice reads a passage, and it's a well-designed passage so that it covers all different types of so approximately 2 to 5 minutes of talking just once is fine for the primary use. Now for the secondary cases, like negative examples, it's really almost impossible to train the system with all different types of negative examples. At the same time, it's not really required in our system. As long as our system, the way it classifies it finds the closest match, and at the same time, it has a threshold. So after sound source separation, it just finds out Alice's voice. That is the primary sound. So we don't really need to know or classify the secondary sources. So that way, the short answer is that the primary user, the main sound, the main speaker needs to talk to the system for a maximum 5 minutes. A standard script is used, and that is fine. That's what we did for our results.
Okay, we have time for one more question if anyone has them. Going once, going twice. If not, I want to thank you again, Nirjon, for your talk today. Really interesting stuff. We appreciate your time, and we appreciate the time of all of you in the audience who spent time with us today. Remember that DataBytes is a monthly lunchtime webinar series presented by the National Consortium for Data Science. We do skip the month of July, and our next session will be Wednesday, August 2nd at noon, and the featured speaker will be Marcello Balducini. I'm hoping my Italian pronunciation is correct there. He's an assistant research professor in the College of Computing and Informatics at Drexel University. We hope you will join us again for that talk. Until then, thank you. Have a wonderful rest of the day. Thanks again, Nirjon.
Thank you. Bye-bye.
Bye-bye.